Morning, everyone. Thanks for attending today's EORI Insights. My name is Roger Hillbush. I'm the Deputy Director of the Enhanced Oil Recovery Institute. For those of you familiar with EORI and our Insights events, if you've attended one before, welcome back. If you haven't attended one of our events before, or not that familiar with EORI, I'll take a quick moment just to briefly explain who we are and what we do. EORI was established as the operating unit of the Enhanced Oil Recovery Commission, also known as EORC. EORC was established in 2004 by state statute. It's a state-funded agency, and the EORC oversees and provides all the strategic planning for Enhanced Oil Recovery Institute. The mission of the Enhanced Oil Recovery Institute is to collaborate with Wyoming oil and gas operators, provide technical expertise to minimize stranded oil in Wyoming fields, and to extend field life, and to add revenue to the state of Wyoming through taxes from additional production, incremental production. The EORC consists of 8 commissioners. 3 of them are ex officio. One includes the governor of the state of Wyoming. The other is the state geologist. And the last ex officio is a state legislative member. The other 5 members are appointed by the governor and include one representative of the University of Wyoming, one representative from the Wyoming Oil and Gas Commission, and the last 3 are representatives from the oil and gas industry. One of the things that EORI does to uphold their mission is we provide outreach and host little events like this one, little focused events such as this EORI Insights. EORI Insights we developed to engage and inform industry with any new resources or processes or technologies that might be of interest and benefit, that might benefit you. Today's Insights is the 3rd of the 4 that we're going to be hosting this year. The Insights events we try to hold quarterly throughout the year, and today's is the 3rd event that we'll be holding. For today's Insights event, we welcome Mr. Mark Wolf. Mark is the CEO of Wolf Process Technology and is founder of Wolf Process Technology, and has a degree in petroleum engineering from Texas Tech University. And Mark has designed and built process equipment and facilities for over 30 years, has 8 granted and 2 pending patents. With an extensive background, both produced water treatment and solids handling, he started Wolf Process in 2020 to provide cost-effective systems for handling oil field solids. Mark is active in the Society of Petroleum Engineers and the Produced Water Society, serving on the SPE Production and Facilities Technical Advisory Committee, the SPE Distinguished Lecturer Committee, and is a regular speaker at SPE and PWS events. Please welcome Mark Wolf.
Thank you very much. And welcome everybody this morning. Thank you for the invitation. Thank you to the Institute for giving me the opportunity to speak to you today. Again, my name is Mark Wolf. I'm the founder of Wolf Process Technologies. I'm going to talk today about solids handling in production systems. That's what our company is focused on. And I just want to give a little background. The technology that we introduced that we call the Octopus, and I'll explain why in a minute, has actually been around in the industry for 30 years. The origin technology started in the North Sea, UK sector, back in the 80s and 90s as those wells were starting to mature. They were all, the original completions were screen completions. It was an unconsolidated or slightly consolidated sand reservoir. And as the water production started breaking through, they started seeing screen failures and significant sand production. The sand would land in the separators, and trust me, shutting down a North Sea separator to dig a production separator that's full of sand and clean it out, put it back online was a very big deal. So there's a very strong impetus for a better solution. A Scottish company introduced what's now known as cyclonic jetting technology. I'll talk a little bit about different jetting technologies on another screen here in a minute, but it was introduced by a Scottish technology. I joined that company in 2002 to start up their business in the US. So we started in Houston, introducing this technology into the oil and gas industries. We did well in highly engineered facilities, offshore platforms, facilities where you have 9 months to 15 months to design and build a facility. And the capital budgets were quite a bit better than what they are in most traditional onshore field. We tried for years to introduce our technology into the onshore market. Money speaks. It was very, very expensive. It was also very long lead and highly engineered. So a typical delivery might be 4 to 5 months, where an operator in the Permian or Wyoming is ordering a separator and expecting it to 6 to 8 weeks. It just didn't fit. So the emphasis, or the economic emphasis, was, can we do this in a way that fits the onshore market and expand adaptation? It's a very important technology, and I'll explain why in just a second. Okay, let me see. I was just given instructions. I need to share a screen, so bear with me just a second. Let's see if I need to share this screen. Would it not be this one here? It's the screen too. Okay. All right. And then play. Thank you. Maybe I didn't click it. There we go. Okay. All right. So I'll move on past the introductory screen. So cleaning a tank or a production separator is still one of the most hazardous jobs in the oil and gas industry. I have a little statistic here. This is not oil and gas specific. It is across the US, but from 2011 to 2018, over 1,000 Americans, 1,030 is the exact number, lost their lives in confined space related industrial incidents. That's an average of about 130 people a year that died during that 8-year time period, entering confined spaces and doing their normal daily job. I went to look, what's a comparison, something that's a little more sensational. So I thought, okay, tornadoes and hurricanes, those are dangerous. They kill a lot of people. So I went and looked up the statistic there. On average, in an average year in the US, 80 people lose their lives to tornadoes and hurricanes. So for that 8-year period, we killed more people sending them into tanks and separators intentionally than people getting hit by tornadoes and hurricanes across the United States. It's a significant number. It's an important number. Now, we have a really good track record in the oil and gas industry. It's rare that we have a fatality. It's not so rare that we have near misses or incidents. And I'd like to share one incident. This is a story I heard recently from a good friend of mine who runs tank cleaning business. There was a company cleaning a tank. It was a large tank. Solids had accumulated 8 or more feet in a tank. Young kid, 19 years old, just out of high school, decides he's going to go into the oil and gas industry because that's where the money is. Got a job with a tank cleaning company. They did everything right. He was under air. He had a tether. He had a Tyvek suit on, framed. He went in. He was cleaning out the tank with his hose, and a wall of debris gave way. He slipped, fell, completely buried. The crushing weight of one of the most horrible sludges that you can imagine. There was a rescue team nearby. They were trained. They knew what to do to recover him. He was under air, so he was still alive. They knew they couldn't just tug on his safety tether because that could rip the mask off his face and kill him. So they had to dig him out. They were quick. They got him out in under 10 minutes. He survived, went to the hospital to check out. He's okay, a little shaken up. But we call that a success story. He didn't show up for the next day. He left the industry. And I'm sure he's still dealing with the traumatic impacts of that day. So injuries aren't always physical, and it's difficult to count the toll that kind of an incident happens, and they're still happening today. This is partially what drives us, what drives me to introduce this technology and talk about it. Of course, we're a business and we're expected to generate a return from our investors and for ourselves, but there is an important story behind what we do and why we do it. So I started off talking about, excuse me, let me take a quick drink of water. I started off talking about the economic side of this technology, and that's important because if we can't make the economics work for you, in spite of the safety issues, in spite of all the rhetoric that we hear that safety comes first, it doesn't. It doesn't. Money comes first. It's a business, right? We've got to make things. So our goal has been to make this an economically attractive solution so that operators can start to clean their tanks and vessels without sending people inside of them, without having to shut down production. That's what we're doing. Excuse me, I'm a little passionate about that piece of our story. So this is a good success story. So this is an operator in West Texas. We install our technology, and I'll get to the details of it in a minute. I'm sure lots of you want to know technically what is this thing. So we use thermal infrared imaging to detect the level of solids inside of tanks and separators. It works because the solids are an insulator. When they settle into the bottom of the tank, they insulate the shell from the warmth of the process fluids. So now, if a vessel is offline and has equalized in temperature to the air, it doesn't work, of course. But when a vessel is live and you're flowing fluids through it, usually our well fluids are warmer than the outside environment. The warm fluids will light up the shell that's not covered up with solids. So we can very clearly see the solids, and you can see profiles. It's really amazing. Simple tool. $400 for a camera that attaches to your iPhone now. That's how cheap it is to go out and get these. So if you know anybody that's dealing with it and they haven't already adopted IR technology for looking at levels of solids in tanks, they're behind the time. That's simple stuff. But this is the image on the left. So we installed our Octopus in a 10x40 production separator. This is in the Permian Basin, in the Midland Basin area of the Permian Basin for one of the major operators. And we told them, install this technology, it will dig itself out. And there was an operator who I think, you get these guys who want to prove you wrong, want to say, okay, we're going to try this and then we're going to make sure it doesn't work and we won't have to worry about it again. So he intentionally waited until we kept calling, are you ready for us to clean out? You should be ready for us to clean out. He waited and said, okay, you can come clean out now. And he gave us this vessel on the left that was completely full of sand. Good challenge, right? So we hooked up, we ran the system, and in under 4 hours, we gave him back the vessel on the right. He didn't shut down. He didn't slow down. He didn't change any of his valves or his operating pressures. It was all done online without ever stopping or deferring production, without cracking the vessel, without sending anybody inside. He's got a vessel that is fully operational and clean and ready to go. That's what we're doing. And we're doing it at a price point where it makes economic sense to do so regardless of the safety. How did we do there? So just a little background, and I promised I like to try and give some good content, not just a sales pitch. So I've got a few bits of technical information in here that I'll share with you. So what we're looking at is a typical production system. They're all a little bit different, I recognize that, but a typical production system where your first step in separation is your primary separator. Sometimes you'll have a test separator in line, but for the most part, you're going to into a primary separation vessel. It's usually a pressure vessel, although there are some exceptions in stripper wells. But this is the first place where sand wants to settle out. Sand is heavy. So, and again, we're not talking about just sand. Sand is prevalent in the Permian Basin where they're fracking wells, but in other areas, it's other types of solids. So if I use the word sand or solids, I'm using them interchangeably. So please forgive me if I do. But the solids will settle out in the first spot where the momentum slows down. And that's usually the production separator. It will build up if unchecked, and then it will start to carry over. You may see some decline in separation efficiency. You may see more emulsions, more bad oil coming out. These are all signs that solids are starting to accumulate in your production system. The next step is it will follow carryover with the water. And generally that happens pretty quickly. So wherever your water goes next, in this diagram, I've got it go through the gun barrel tank, which is pretty typical in West Texas. It may go to a free water knockout. If you're in high water production areas, free water knockout may be the first thing in your system. But again, this is just general in nature. So their problems with sand carrying over with the water are, the number one problem is damage to level control valves, separation valves. Between the separator and the gun barrel or whatever is downstream, there's a pressure differential. And we have to hold that pressure back and let it down, take a pressure drop, usually is across a control valve. So the control valve is generally the first casualty of sand carryover in the water system. When you have those control valve failures, there's oftentimes an issue called gas blow-by. So if that valve fails, the level inside of that separator drops, and then the gas can come out with the water system and go into your atmospheric water storage tanks. That's called gas blow-by. That is what's classified as a super emitter for methane emission. It's not happening every day. It happens intermittently when there's an equipment failure. But super emitters are responsible for over 50% of methane emissions in oil and gas production operation. So that's the number two issue is maintenance and emission sources from sand accumulation. A very real story, if it accumulates far enough in the separator, like that image that I showed you in the first infrared system, it can get over the oil weir, which is pretty high up in the vessel because the oil floats and it's going over. But when the sand starts to cross the oil weir, now you're sending solids into, typically it's a heater treater where we're trying to refine the oil and get the rest of the water out. Solids and heater treaters are a very dangerous mix because the solids now can sit on top of a fire tube. If you're familiar with what a heater treater looks like, it's either a horizontal pressure vessel, sometimes a vertical pressure vessel. There will be a tube through it, and we literally, it's like a gas burner, and we're using that to heat the crude inside. So the skin on that burner can get warm, but it's transferring its heat to the fluids around it, so it doesn't overheat. But when you get solid settling on top of it, again, they're an insulator. Now the skin tube on that fire tube gets very, very hot. It exceeds its yield strength and it collapses. Now you have a flame introduced into a vessel full of oil and you get a fire. And this has happened. One of our major customers, an international company operating in the Permian, our first customer in the Permian Basin, was driven because they had just such an incident happen. Their heater treater burned down, cost them $20 million to fix that problem that was associated with solids production. So these are very, very real cases of what solids accumulation can do inside of a production facility. There's a couple of other items on there. I don't have any great stories to tell. I think that's enough to get the story across. The point being is if we put online solids removal in that first step in the process, we can stop the carryover, we can control the solids accumulation at one point in the facility. You'll still get some fines that don't settle out that will carry over and over time will collect in these other vessels, but it cuts it down by orders of magnitude. So it's a good place to solve the problem in production facility. Let me see. Are there any questions so far? I'm kind of expanding a little bit. That's a trip because I need a drink of water. So anyway, now would be a good time. Yes.
How much of solids can you control with your technology before they enter the separator?
I hope to answer that question through the course of the next slides. Okay. And if I haven't answered it, please ask it again, because I have some good visuals that I think will help answer that. So just a little background on technologies. I got two diagrams. The diagram on the left is traditional sand jetting technology. It's been around for many, many decades. I've seen references back into the 70s. There was a good paper presented in the 80s about how to design a sand jetting system. In general, sand jets are, I'm going to call them linear sand jets. We're introducing high pressure water through a small opening, jet, classic jet, using a pressure washer approach to sweep sand from across the vessel floor to a central drain point. That's the theory behind it. A lot of problems with traditional sand jet systems, which and they were installed in the North Sea from the original designs, and they failed. They didn't work for a number of reasons. One, the sand jets can very easily become plugged. They have to be fed with a water source, and oftentimes that water source will be coming from a tank that itself has solids accumulation in it, and it recirculates back through and plug a sand jet. When that happens, that extra pressure has to go out through other jets, which raises the velocity that that jet is producing. So you've got erosional impacts on a vessel wall. Number one problem. Number two problem is if the solids level is allowed to accumulate above the level of the jet, they don't work because you cannot get enough pressure in there to remobilize all of that solids. And from a practical design standpoint, they require a lot more pressure. So a typical sand jet system may need 80 to 100 PSI of pressure at the jet to get enough velocity to liberate that sand and move it across to a drain. So that's an operational consideration. If the separator is operating at 150 PSI, now you need 250 PSI water pressure. You can find it, you can create it. It just adds to the capital cost. I think I've covered everything. But what I'm showing on the right is cyclonic jet. This is the technology that I said originated in the North Sea, and this is our version of it. I'll talk about materials in a little bit, but we make our cyclonic jets out of high density polyethylene. The way a cyclonic jet works is we introduce the same motive water into, I will use the pointer now. So we'll introduce our jetting water, our motive water, into the side. This is the device is essentially a tube, which is our solids discharge tube, and it's surrounded by an annulus that has a conical shape. So we introduce the motive water into the annulus on a tangential entry, like a hydrocyclone. It looks a lot like a hydrocyclone, and that creates a swirling spin inside of that annulus. The water is discharged. It hits a diverter foot, so it gets discharged parallel to the floor of the vessel, and it creates an outer swirl. That outer swirl drives a vortex under the tube, which lifts solids. And I'll show a couple of videos, so you can see what this looks like. But that very simply is how it works. For comparison, we need about 6 to 9 PSI at the inlet to this cyclonic jet. I also use the term VFU, which is our acronym. It stands for vortex fluidizing unit. So if you hear me say VFU or cyclonic jet, those are interchangeable. So much lower pressure because the point where we're introducing the water is directly adjacent to the point of discharge. We're not having to send water across a vessel. Think about this for a minute. The energy of these jets dissipates very rapidly. Picture yourself sitting in a jacuzzi. It's got a jet against the wall. You back up against it. You feel it very strong against your back. You move away a few inches, and then it reduces to a tickle. That's how fast that energy dissipates, which is why jetting across a floor, it takes a lot of pressure to get any kind of velocity where you need it. In this case, we don't need nearly so much pressure. The water's introduced right where we're pulling up. It can work when it's completely buried, and I'll show you some video. This is just some add-on information to what I've already said, so I'll just repeat what I've said. The image in the upper right, this is an actual sand jet system that we replaced. This was our serial number 1 we did in California. The customer had a sand jet sitting system in his vessel, wasn't working. You can see the blocked sand jet header hydraulically, and I'll share some information about piping design, which may be helpful if anybody in here is a facilities engineer or production operator. That will be helpful. But in general, when we're looking at piping systems to carry sand, we have to pay a lot of attention to the velocity. So a sand jet header is a header with a bunch of jets coming out. You introduce water at one end of this big piece of pipe, and it's flowing very quickly. And as you go towards the end of the pipe, water is going out the jets. By the time you get to the end of the pipe, the velocity is very, very low. So these solids start to drop out. And rather than going out through the jet, they'll accumulate in the header. And that's another factor that contributes to plugging and failures. So this is a case where the sand jet header had become blocked. The jets had eroded a spot in the wall. Very expensive for them to fix. Had to go in and strip the coating, build back up the damaged area, and repair the vessel. So, okay, this is the first video that I share, so I'm going to just introduce it real quickly. What you're seeing is our cyclonic jet, or VFU. It's going to start where most of the sand has been removed, so we can see the swirling action, and then it's going to flip to showing full of sand. But let me just give this a start. So we're introducing the water. It's hitting the foot, and you'll see how it sets up a swirling motion that disrupts the sandbank, and it's like undercutting in a mining operation where you're digging sand out from base, and it sloughs into the area of influence where it can be pulled out by the vortex that's under the discharge tube. You can see this is we're generally flowing at about 25% by volume with this sand. That I won't get into the technical details of why, but has a lot to do with particle size and characteristics of the sand itself. This is my favorite scene in the video. That's about 3 feet deep right now. The picture I showed at the beginning, that was about 8 feet deep, and we were able to dig that out, but very effective at removing solids when it's completely buried. Any questions to this point so far? I don't know. Is there a way for the online folks to ask questions?
Yeah, they've got there's a chat they can ask.
Okay, if you're online on Zoom and you have a question, we're monitoring the chat box. Feel free to type in a question and we'll stop and answer as best we can. So this is just some more technical stuff, but I like the video here. This was actually done by a colleague of mine who's been in this field for a while as well. It's very quick. I'll show it again. But this shows the vortex forming underneath. Let me go back. This shows the vortex forming underneath a cyclonic jet. You can see it's quite effective at pulling sand up from the bottom and lifting it in. If you think about a vortex or a tornado is a great example. The winds that are out away from the vortex are slow, and as you get closer, they get faster and faster and faster because you've got the same mass of air trying to move in a much smaller space. So it has to move much faster. It gets acceleration. It's like swinging a rope with a coin on it. As you pull it in, it's gonna move faster and faster. Just simple acceleration due to shortening the radius. And that's how we generate our velocity. That's why we're able to generate enough velocity to lift solids from the bottom without a lot of pressure. It's using vortex. Little technical bit for those of you who are technically oriented. So, okay, so that's the basis of the technology. But what our goal has been to reduce the cost. So I'll talk about how we did that. So what you see in the upper left of this screen is the way we used to manifold these devices together. And it's important to manifold them inside of a tanker vessel because each one of these jetting units has a 1-inch connection in and a 1-inch connection out. And each one will affect an area from between 3 and 6 foot diameter. So we're covering a large area. We need to put a bunch of them together. We have to manifold them. The way we did this starting back in the 90s in the North Sea was we engineered these mirror imaged piping systems. If you look, I'll use the pointer again because I think it'll be helpful. If you look at this image up in the left, and let me just explain why. So when we put multiples of these on a manifold, it's important to achieve what we call hydraulic balancing. So the pressure loss from each device to the point of discharge of all of the devices needs to be the same. If they're not the same, will have differences in pressure loss, which means one device will pull more and the other device will pull less. So we have to hydraulically balance them. That's why these complicated piping manifolds came into play. And if you look, the distance from each one of these jets and the configuration to its point of discharge is the same. Again, we're using symmetry and mirror image type piping networks and growing the diameter of the piping until we get to the point of discharge. Every manifold that's built like this has to be custom engineered and custom manufactured for a specific spot in a specific vessel. So that takes a long time and a lot of money to do. Typical engineering time, maybe 4 weeks, 6 weeks. By the time you get through approvals and the entire delivery process, it's at least 16 weeks to deliver a manifold to site. It's all made from stainless steel. You can't make it from lower alloy metals because they'll corrode. They have to be custom manufactured. The materials are expensive. Another thing we discovered is that when you weld pipe together, you're generally doing what's called a penetration weld, which is a high energy weld, and that generates weld beads on the inside and disconformities. So it's not perfect. So what we did, we said, first thing we want to look at lower cost materials. There's a tremendous amount of evidence in the literature that said high density polyethylene is a great material for transporting slurries. There were anecdotes we heard. We dug deeper and looked into the literature and found some good technical research that had been done. And the theory goes, and this is actually proven out in some experiments, is that if you look at erosion of materials, if you've got a sharp-edged particle of sand, the first thing you want to consider is the energy of impact against the vessel wall. So the faster it goes, the more energy, or the larger the particle, the more energy. When that particle strikes a rigid material like a steel, it chips away at it and exposes an area for corrosion. By contrast, when you look at soft materials like polyethylene and rubbers, that impact energy is absorbed and reflected. So rather than chipping or scarring the material, it's reflected back. It's resilient. So contrary to what your intuition might say, everyone says you need a harder material. There's a certain range where a softer material is actually more advantageous than a harder material for erosion. We did a lot of material research and said, this is a great material. We set up our own lab. I don't have images of it here, but that's in the expanded version of the talk. But we set up our own lab. We tested it, proved itself out. We ran cycles. There were no material off in our HDPE system. So we went with HDPE. The second challenge we said was, well, HDPE is not rigid like stainless steel. How are we going to build a manifold like that out of HDPE? It's going to look like spaghetti. So that's where the idea of the octopus came in. So we went to a hub and spoke type of manifold. And what we found is that by connecting the jets to our distribution hub with flexible lines that are all cut the same length, we can achieve hydraulic balancing. There's no internal disconformity from welding. We've got a nice smooth pathway from the device to the distribution and collection hub. And we can eliminate our engineering. Now, all of these materials are kept in inventory. The hubs are the same. The BFUs are the same. The flexible pipe comes in a roll of 100 feet. We take it out to site and we cut it to length and install it. So we've taken what used to be a 16-week process down to a couple of days. We can get a call from a customer. Here's our vessel drawing. What can you do? And we can be on site within 2 days with materials ready to install. So this is a tremendous win for retrofits. I'll show you some other things that we've done for retrofits as well. But when you're retrofitting, an operator says, we've got a vessel full of sand. Maybe we should try that octopus thing. Oh, how long is it going to take? 16 weeks? Yeah, forget about it. How long is it going to take? We can be there in 2 days. Okay, we'll set up the clean out crew, come out and install for us. So we can do retrofits. And I'll show you some other things that we've done to make retrofits even easier. This is an important part. Did I get that concept across well? Do y'all understand the advantages of the hub and the full pipe? Does that make sense? Question from the audience, Shane?
They're behaving
They're behaving
quite well.
Behaving quite well. Okay. Okay, so this video is already running. Before I get a chance to introduce it, I'll rerun it. So we looked at materials, commercial materials, and we found PEX. PEX, you may have heard about it. We're using it everywhere in houses. In Houston, a few years ago, there was a hard freeze. And for Houston to have a freeze where the temperature stays below freezing for more than a day is rare. It stayed below freezing for 2 weeks. In Houston, they build all the houses with piping in the attic. Excuse me. Pipe froze. They're mostly made of either PVC or copper or some other rigid material, and they broke. But he knew that their pipes were broken because it was frozen. They didn't have power. There was nothing to heat their house. They lost power. It was horrible. The whole state lost power for many, many days. Temperature started to warm up. All of a sudden, we have a lot of repair work to do in Houston. So PEX had been in the market in new construction, but now they found a pretty good retrofit market. It's commonly available, and it meets all of our operating conditions. The other thing that's great about PEX is they have a connection system now that doesn't require any kind of metal whatsoever. There's no clamping rings. It's something called an expansion joint. You take the end of your PEX. There's a reinforcing collar that's also made out of the PEX. The tool expands the joint out. You slip it over a bar, and in about 8 seconds, you can make a connection. Let me replay this now, and you can see this live. Just hang on. Sorry. Hi, my glad. Sorry about the interruption. There we go. Run that. So you can see a joint being made where he's using the tool to expand out the joint and slip it over the bar. So that's how quickly the joint is made, and there's no metal. We used to put these things together with flange joints inside of vessels. With a flange joint, you've got to use stainless steel bolting. You can't use a carbon steel bolting. You put stainless steel against carbon, you set up the potential for dissimilar metals corrosion. It takes longer, all sorts of problems. So we've taken the problem of actually, and when you're working inside of a confined space, we still have to go inside of these vessels to install them. We make sure that they're cleaned out to what's called a level 2 environment, meaning it has an atmosphere that's safe, so we don't have to go in under air, and we've removed the hydrocarbon. Still, working inside of a confined space is difficult. It's really the floor is shaped like this. It's not flat. It's easy to slip. So we want to make it as easy as we can and as quick as we can to do the installation. So that's one of the innovations we brought to this technology, is to make the installation quicker and easier. And this joint has done it for us. The image on the left shows a fully installed system. You can see our main piping coming in from the vessel wall and exiting the floor. Our VFUs spaced out. So this talks about another innovation that we introduced. So we used to have to have, you've got to support all of the stuff inside of the vessel. And generally we would weld on what we call a clip, just a little metal piece that you can bolt something to. If you're in a retrofit situation, to install a clip, you've got to grind away the coating. You got to go in and make the weld. And if this is a code vessel, now you got to bring out an AI inspector to re-inspect, re-hydro test. It's a long, arduous process. It's really makes it prohibitive to do retrofits if you've got to weld in supports. So we introduced a magnetic support. So all of our VFUs, as you can see, have Viton coated neodymium magnets at the feet. Each magnet, this is our original magnet, had about 70 pounds of pull force each. Now we've gone from a round magnet to a rectangular magnet, and I won't go into the science of why it gets the magnet closer to the vessel, but it does. It goes right on top of the coating, and we've got a lot of holding force holding those pieces in place. So another innovation made it quicker. Our crews go in, they measure out, they mark with a Sharpie on the floor where they want it. They put down the VFUs, they stick like glue onto the vessel floor because they're steel. We've done some tests with one of our customers. They wanted to see what the condition of the coating was after it had been in service. So we went in and removed. Coating integrity was good. So we know this is a great innovation for this space, to be able to speed up the installation and reduce the time that people have to spend inside of inside of the vessel.
Mark,
Yes.
I don't have a sense of scale. How
Okay.
big are the VFUs, generally speaking?
I wish I had one. Okay, so sense of scale. The VFU with the magnet, the VFU itself is about this big. That whole piece standing is about this tall and maybe this big at the base. Okay. This is inside of a 10-foot diameter vessel that you're looking at. Okay, just a little bit on materials. We do have some material options. The base material that we have in inventory is high density polyethylene and of course the PEX. The HDPE is rated to 180 degrees Fahrenheit. That fits most applications that we need. We're also doing some high temperature work up in Canada in the SAGD area. Great EOR method that the Canadians brought to the world. They have much higher temperatures, so we do everything in stainless steel. Same style of hub. We're using convoluted flexible stainless steel in lieu of the PEX. So no piping in the high temperature stuff. There is room for intermediate material in there, which we're calling nylotron, but we're very, very close. We will eventually be able to replace the HDPE with the nylotron and just have one material for the base. But at the moment, everything is still HDPE. It's more readily available, a little lower cost material. We're at the point where we're machining our components. We haven't yet gone to molded components. So it just makes sense for the market that we're in now. But there's still room to reduce costs further, and we're working on that. Any questions before I talk about applications? I think I've covered the technology as well as I could. Again, that's my trick, so I can get a drink of water.
So are you using this application? I mean, it's a pretty neat concept. So it's just for the onshore, or are you also using offshore? I mean, you mentioned North Sea and Canada. So what percentage of your products are being used by high temperature thing and
And I have a couple of slides that I'll talk about there. We've innovated outside of the vessel, but in general, if you look at the capital cost of what goes inside of the vessel versus the CapEx for a typical offshore project where you have to automate all of the piping, there's sequences. There's water goes here, and then slowly comes out. There's valve sequences to deal with. That's either a man sitting there doing it that knows what he's doing it, or a computer that's automated. But when we looked at those costs, the cost of the external piping with a full automation was 85 to 90% of the total CapEx. So one of the other about some applications first, just show you some pictures of what it looks like, get into a little bit more detail. This is an example of a new build installation. It's a lot easier to see in a rendering and a cutaway than a picture inside. So, but this is a system that we've actually installed and about to commission. You can see our magnetic support, VFU. Again, that's the cyclonic jet magnetically supported VFU. This is still the old round magnets, but we're using rectangular magnets now. And the other thing we'll do in a new construction is we'll supply let me use the right pointer. We'll supply a fabricator with this little, this little piece in red. It's very inexpensive. We ship them to the fabricator. He welds them to the inside of the welds that couple into the vessel shell. The entire thing gets coated inside and out. We coat across the bars. These are I'm using my pointer, excuse me, online people can't see where I'm pointing. These are the barbs that we use to make up that PEX joint that I showed earlier. So the larger pipe is also an expansion style joint. That gets coated before we put the joint in. So the joint's going right on top of a coated barb. So there's no exposed metal. There's no stainless steel bolting in the joint. It's very robust from a corrosion standpoint. So those get installed. We're using a different style of hub. We're using what we call half hub. So there's a hub on the slurry discharge and a hub on the motive water. It just makes it's lower cost again. It makes it easier to pipe. You can see sort of an engineered drawing of what that lid-on piece looks like on a long, what's called a long well neck flange. That's a term that facilities engineers will know. The rest of you may not. It's not important. When we do retrofit, so we're having to work with nozzles that are already there. We don't want to cut new. Rarely do we want to cut new nozzles onto the vessels. There are cases where it makes sense. But usually there's a drain nozzle, there's some kind of a spare vent nozzle or an instrument nozzle that we can use. So we've developed flange adapters that can turn an existing nozzle into a process connection for us. That gives us our barb on the inside of the vessel and also can extend. For instance, the adapter on the left is what we'll use on drain flange, most commonly on drain flange adapters, but it can be used on any process connection where we get our process connection straight through to the bottom where we can connect in our piping for either a motive water or a slurry. We also retain that connection to the vessel through the annular area of the T. And then that has to be stainless steel, so it's more expensive. For if we have a nozzle that's just not being used for anything else, we can use our Stinger style adapter, which is a coated carbon steel adapter. We'll also a lot of times add a gear or a dam to stop solid from because they'll migrate along the bottom of the vessel to the water. So in some cases, we'll add a magnetically supported sand weir or sand dam into the vessel. In the image I showed, I didn't point this out, but in the image I showed a minute ago, you can see the sand weir right here in the vessel. And this was something that was put in because the vessel was new. This is a heater treater application. So I get the question, your PEX is rated to 180 degrees and you're putting us right up underneath a fire tube that obviously the flame is at much higher temperatures. But the materials that we're using don't see those temperatures. It's kind of like when you're sitting outdoors at a restaurant, it starts to get cold and they turn on the heaters. If you were to reach up and touch that heater, you burn yourself. It's hot right at the surface, but that heat dissipates. So you're getting some radiant energy. When we're flooded underwater, the radiant energy dissipation is a lot higher. So your temperature of the fluid bath equalizes really within a few inches of the fire tube. So even though, so what we look at is what is the planned operating temperature, or the max operating temperature of that heater treater vessel. For those of you who don't know this term heater treater, if you're not spending a lot of time in production, that big pipe, that's the heater tube that I talked about that I mentioned earlier. We're talking about tube burnouts. So you can imagine if solids settle on the top of that tube that they can cause a hot spot. Now we're not preventing solids settling on the top of this tube. This is a secondary case where the solids are being carried over in the oil and they'll get released. It's not carried over through the water. A lot of people ask about tanks. Yes, we do tanks. This is an example of a tank. I think this is maybe a 16 or 20 foot diameter tank. It's got 2 sets of octopus 8 total BFUs. That red circle in the center, our customer just said, hey, we have a high velocity area. He was doing something special. We want to keep everything outside of it. That's why you see it in the drawing. Not really relevant. We'll tend to spread. So I mentioned the zone of influence of a VFU between 3 feet and 6 or so feet. If we're in horizontal vessels where we always have a little bit of solids accumulation that remains between the fluidizers. It's not doing a clean sweep of the vessel, although we get pretty close. We call that the residual sand profile. When we're in a horizontal vessel, we like to have the spacing much closer to keep that residual sand lower. If we're in a big tank, you're not so sensitive to a foot or two of solids in between the VFUs. What you're really doing is maintaining an operating volume in the tank. So we'll tend to spread them out a little bit further. Generally, around 6 or 7 feet around the wall, which is a more sensitive area because that's where you've got your inlets, your outlets, oftentimes wall mounted instruments, level instruments. We want to keep those safe and free from solid accumulation. We'll tend to spread out the spacing a little bit more on the inside of the tank. Again, just making it economic. The more we put in, the more expensive it is. So that's generally what the balancing act that we're playing with tanks. I think I'm going to talk about the operating issue next. This is a little bit of educational information if anyone is interested. I think we've still got a little bit of time. I mentioned this earlier. I see the same mistake made over and over again by trained engineers designing facilities just because they're not as familiar with designing piping to carry solids and slurries. So I just have 2 slides and 2 important items that I want to touch on. So the first slide talks about how solids get transported in a slurry. What I've shown here are 4 different phases. High energy is on the left, low energy is on the right. So if you're and high energy means high velocity, translates to high velocity. So if we're flowing at a very high velocity, those solids will be completely suspended. And there are formulas that help us determine what that is because there are many variables at play here. As we start to slow down, we move into more of a heterogeneous flow where the solids are still fully suspended, but there's a concentration gradient. There's more solids towards the bottom of the pipe than at the top of the pipe. And as we lower the energy further, we slow down the flow rate. The solids will now drop into what's called a sliding bed or a moving bed. So you get a bed of solids that's sliding across the pipe. This is the most erosive condition. So again, it's counterintuitive. If you have a piping system that is operating in the sliding bed mode, the best way to reduce erosion is to increase the flow rate. It's counterintuitive. You think, well, I'm going to slow it down, it's going to be less erosion, but this is a case where that's not true. And then once you drop below what we call our critical velocity, and this is important for the next slide, you get a stationary bed. And that's where the solids start to accumulate and don't move. And that's where you run into issues of blocking. So, and I'm going to bring this home with a certain point. So I talk with engineers and especially operators. They say, we're piping for sand. You've got to make the pipe bigger. No, we don't. So if you put in a small diameter pipe, you're going to plug the pipe. No, if you put in a large diameter pipe, we're going to plug the pipe. The large diameter pipe will be easier to clean if you plug it, but it's more prone to blockage. And this is why. Again, I like to give a little bit of educational content rather than just all sales pitch. So this is it. I hope you appreciate it. So this graphic, let me see if I can walk you through it. I've got 3 different pipe sizes shown, one after the other. This is as if somebody had designed a pipe to go from 2-inch, 3-inch to 4-inch, and then to 6-inch with the same flow rate. So you can imagine if you put so much flow into the 2-inch size, as you go larger and larger on diameter, the velocity is going to drop. The red arrow is the critical velocity. The blue arrow is the actual velocity. So you can see in the first example, the 3-inch pipe, our actual velocity is above critical. Critical is that point where we get a stationary bed and it doesn't move and you start to plug. And I see this all the time when people design manifolds for old sand jetting systems. They'll come out of the vessel with a 3-inch pipe. And typical manifold, if you have a bunch of pipes coming into another one, you're commingling, you go up the line size. That's what they do. They go up the line size. So they'll go up to 4-inch. Then they'll get somewhere else and they go up to 6-inch. I've seen this time and time again in the SAGD operations in Canada. They've made the same mistake for a decade at least. And we're having to either repipe or come up with strategies to add flow to keep the velocities up. But this is very important in piping design for slurries is bigger is not always better. It's all about the velocity. We want to stay above critical velocity. A little bit of educational content. If there's any questions, we can talk about that too, but just wanted to share that. Okay, operating methods. I'm going to take a quick drink. Any other questions before I move to the next section? Yeah, water treatment. So I mentioned earlier that what happens outside of the vessel to be 85 to 90% of the CapEx of a project. And for all the decades that we did this, that I was involved in this with the old standstill designs, this is how we strongly urged customers to automate their systems. And we put in these massive automation systems. This is another project I consulted on in California. I did the process engineering work. You can see the line of automated valves, the pump. It was all expensive. And when we look, and this still makes sense. So in traditional production, where if you're in a sand type formation, where you're going to see sand production for 20 years, it may make sense to make the CapEx investment in the outside of the vessel and let it be automated versus manned. I don't know. People have to run their own economics. When we looked at the unconventional market, where we're fracking with 20 million pounds of sand in a well and getting a few percent of that back, the sand production comes early on and then tapers off. So while they have a big problem for 3 or 4 years, it gets less and less and less over time. So it was much harder to justify those ROIs. So we've introduced into the Permian Basin an operating partner who can eliminate that CapEx, and we pull up with a vacuum truck and a water truck, and we hook up manually with hoses, and it's a manned operation. So we bring the CapEx way down. The OpEx obviously is a little bit higher for a short period of time. The economic gain is tremendous for this type of operator. So we're doing this in the Permian. I don't know if it makes sense in other areas, but it's certainly, even if you do have a long horizon for sand production, it greatly reduces the cost to try. So if you're dealing with cleaning out vessels, again, it's dangerous. We're putting people in harm's way. This is a way that operators in these situations can say, we want to try something new without breaking the bank on a project that we don't have any experience with. So we can operate this manually. We can do it. We can teach you how to do it. Either or, it doesn't really matter. But the whole point is try something new to eliminate those confined space entry clean out. This is just a quick video showing our crew operating. This is actually the very first one that we did. So I was on site and did the videoing myself. But it's just a simple little manifold. We're taking samples. We have side glass to see once we've cleared out the vessel, it'll start to run clean. We can clean out a typical vessel in an hour. The example I showed you was 4 hours because he gave us a vessel that was 9 feet full of sand. Turn that off, turn it over. Hopefully that's the last call. So that's that piece. I've been droning on for a long time. That's the end of my slide deck. And I'd love it if we got any other questions or ideas or things you'd like to talk about.
So what's the lifespan of octopus product that you? It's great, actually. Honestly, it's really good. What's the lifespan of that product?
So the materials are not subject to corrosion. We believe they're not subject to erosion. We've been operating, the system has been in operation the longest. We put it in service in August of 23, so about 2 years. I don't have any data past that, but I believe it's going to be for the life of the vessel. In most cases, I mean, it's certainly going to last long enough to achieve payback and then some. But, of course, I'd like to tell you, you'll never have to replace it, but the oil field, things get broke. We know that. But so far, we've had a pretty good record. Any questions from the Zoom audience?
Not yet. I did put out chat message. We'll give them a moment. They have to type in. They have to type their thoughts. So.
Okay. All right. Feedback. You guys have been quiet over on this side. What do you think? Are you working in these kind of environments? Dealing with? Are you familiar with this issue of solids accumulation? Does it hit anybody? Is it hit home anywhere?
We don't have a lot that I know of. Usually it's after a frac, but resin coats sand at the tail end of its frac, and we have not seen a lot of sand coming back from everything that I've ever heard.
Okay.
So
You know, we used to hear that, in the Permian area as well. We don't have problems with sand. Well, they do, they just have ways to handle it. But that's interesting feedback. What about in conventional production? I've seen with my own eyes in Wyoming, a big free water knockout being opened up and solids just pouring out the manway. So I know it's going to be out there. So
That's my question. You primarily are talking about sand, there's all kinds of other,
it's all kinds of other solids. Yes.
so this works well with
Yes. Yes.
all of it.
Again, the technology itself has a really long history going back to the 90s is when the first systems were installed in the North Sea. And we were challenged. We had systems in the North Sea and Azerbaijan and the Middle East, and everything is a little bit different. One case in particular, I remember their solids particle size was like really, really small. We actually did a test for them before they installed it to make sure that we could move that material. We did a test once where we moved, quarter-inch steel balls, like what goes into bearings, just to see, can we lift this stuff and move it? And yes, you can. So it's proven pretty versatile. Limitations, there are obviously limitations. There are times when solids are allowed to sit for a really long time and they can consolidate, they can cement. You can get cementing factors that will stick between the grains. That can be difficult to remove. Usually, that happens if when they're doing the manual clean out, if the solids can be displaced with a water jet or turned with a shovel, then we won't have any trouble moving it. If they have to go in with picks and chip it out, then yeah, I'm not going to move that enough. So we've been challenged with things like asphaltin precipitates and paraffins, and there's generally a good solution around all of those.
You're putting this in old tanks, right? I mean,
And new.
and right, but in old tanks, I mean, how fast? What's kind of the cost of it to do? Just that, just bulk.
The cost question. Yeah. So more reasonable than you would think. It's not free or cheap,
Right.
but it's more reasonable than you would think. So for example, this system that went into the 16-foot tank is probably fully installed under $40,000. Could be cheaper, but right now I'm at the ballpark to go inside of one of these horizontal ducts. In the new build, it's probably going to be closer to 25 or 30, something like that. So I mean, it's it's not nothing, but when you consider what we're saving, the potential safety wins, the maintenance wins, I think it's pretty. I think we've got a good value proposition for the industry and something to be taken seriously. It's at least worth a try. We've got, as I said, we've got over 160 installations now. We're flipping along at somewhere between 8 and 15 new installations a month right now. Most of these are in the Permian. That's where we've been focusing our efforts today. So we're racking up a ton of operating experience with them too. So. Yes.
If we got a tank battery with say 6 400-barrel tanks, which are 12-foot diameter, got maybe a foot of sludge or 2 feet of sludge in the bottom, how do you get in there? With the manway, it's usually just sitting right on the bottom of the tank. You take off that manway and a bunch of that flows out. Then you go in with personnel and set these things on and put the.
So we got to clean the tank first. You do have to clean the tank before we go in and install it. And for one reason, we don't want to install under air. It's not very nice, but for the very real reason is that the tools we use are not hazardous area rated. So you've got to give us a breathable environment where the LELs are below a certain point. Otherwise, our machines they're not hazardous rated, and so that's a dangerous situation. So we got to clean first to go into an old tank. We do employ strategies. We also need process connections in the tank wall. that can be an issue. Tank may access door, so we can replace that. We get our process connections and still have access to the tank. We have to look at drawings. At this point, we need to look at drawings. I'd love to look at your drawings at your tank battery if you want. We can come up with it.
So where are you taking all these solids you're getting out of the tank?
Where do you take them when you clean out manually? They go to the same place. So the way we operate is we don't run vacuum trucks or water trucks. We leave that to the people that do that. So we're not geared to haul material. They are, and they generally know where to take it. In every location, it's going to be a little bit different. In the fields we're working in the Permian, there are solid disposal facilities around that have been built to handle solid waste from the oil field. Most oil fields are going to have that. I assume. I don't know what it's like up here, but you generate solids from time to time. They need to go somewhere. Our job is to get it out of the tank and into your vacuum truck, and that's what we do. And then your vacuum truck.
So for a continuous operation, are these operators you're working for then setting like a solids catch tank?
You can do that. We're doing that for a customer right now where we're designing a solid receiving tank. Generally, when we're dealing with active flowback, we may be cleaning out on a weekly basis. But when we're dealing with steady state flow, it's more like quarterly. So you got to look at the economics. Does it make sense to set a tank? What's going to be the duration of operation? Is it going to be around for 20 years? It may make sense. And then you can run into that tank. And then when you've accumulated enough solids in the tank, you can bring in your vacuum truck and run the operation there. So it gets to be site specific how we work out some of these details, but we've generally found a solution for most of the operating situations we've encountered so far. And sometimes it makes sense to automate, to put in that CapEx, to automate, have your tank, and then let it run on a daily basis. Our first installation in the Permian actually did that. It was one of the majors. They put us into a separator and said, we want to fully automate it. They set a catch tank and it runs every day, twice a day. They have no solids accumulation because we're keeping it clear. And then as that tank fills up, they'll come around maybe once a quarter, once every 6 months and pull the solids off the tank. Great.
Doesn't look like our online attendees had any questions.
Okay. Is my contact information anywhere in there? Would you
We do have it on our website.
you have it on the website? Yeah. Okay. If anybody wants that, reach out to me, or if you've think of something after the fact, please reach out to me. I'm on LinkedIn. We're on LinkedIn for us. I would appreciate it if you find us on LinkedIn and follow us, maybe help us get the word out. Again, although we're a business, we're, commercial, we have an important mission, and that is to reduce the number of confined space entries we have to do. There are times when you have to clean out a tank. Sometimes you have to inspect it, sometimes you have to repair it. We're not going to eliminate that because you still need to do that. But we're targeting the elimination of the production clean out, where you've got to clean out just because you're making bad oil, you're getting carryover, you're getting maintenance problems. It's expensive and dangerous when you do have to do it. So let's eliminate those clean outs, and that's going to be 80 to 90% of the confined space entries that we're dealing with in our industry. That can have a huge impact on our state statistics, and we could send guys home not only without physical damage, but without the emotional trauma of being buried under a wall of sludge. So look forward to follow us, please, and help us connect to more folks in the industry and let them know that the solution is out there available. Thank you.
Thank you, Mark. Very, very technology, especially. I'd like to thank everybody for today. I'd also like to extend my thanks to Troy Oil Companies for their continued support of EORI, letting us use this meeting facility for these events. I'd like to recognize my business and technology team as well, Kelly and Shane and Gabe, for developing and hosting these events, doing everything that needs to be done to make sure they're running smoothly. As this concludes our third Insights event for this year, our fourth is scheduled for October 28th here in this facility and online at 8 a.m. to 10 a.m. We'll be hosting Dr. Jeffrey Thine and Teresa Nealon, who will present on eCell patented engineered salinity technology. So to find out more about that next event, you can go to our website to register for it, get more information on it. If you're interested, you can also get more information